Good evening everyone. My name is Devlina Maiti, a research scholar in the Department of Mathematics, IIT Kharagpur. And this is the sixth problem solving session for the class Basic Real Analysis. Let's wait for a few minutes, then we'll start. Okay, so let's start this session. So in the last session we have discussed about continuity and uniform continuity, and in this session we are going to discuss about differentiation, so in this session we are going to discuss about differentiation and their property. Okay, so let's start this session. So the definition, so let I is a subset of R and f is a function from I to R. Let C be a point of R. Now we say that f is differentiable at C. So f is differentiable at the point C if the limit x goes to C, fx minus fc by x minus c exists. then we'll say that f is differentiable at C, and we'll write this term by f dash c. F dash c equals to this limit. Okay, and this number, this term, this fx minus fc by x minus c is nothing but the slope of the line segment joining x fx and c fc, right? So if this is our fx, some c, so this is x fx and this point is c fc. So the line segment joining this 2 point, the slope of this line segment is this fx minus fc by x minus c. So when x approaches c, x goes to c, then this line segment will be the tangent of this curve at the point c, right? This is the geometric representation of this differentiation. Okay, now we'll say that if a function is differentiable at a point, then it will be continuous at that point. Okay, so this is then f is continuous at c. So for all x belongs to I, which is not c, what we have? We have fx minus fc, we'll write it as fx minus fc by x minus c into x minus c. Since x is not equals to c, we can write in this way, right? Now since f is differentiable at c, this limit exists, this limit x goes to c, fx minus fc by x minus c, right? So since f is differentiable, the limit of this limit x tends to c, fx minus fc by x minus c exists. So now if we take limit in both sides, then x tends to c, fx minus fc is what? Into limit x tends to c, x minus c. Right? Now this limit exists, this one. This exists, and this is nothing but f dash c, right? This one, since f is differentiable at the point c. So from this, it becomes f dash c into limit x goes to c, x minus c, which is nothing but 0, right? So it is a finite number into 0, so it is 0, right? So this means limit x goes to c fx is fc. So it implies that f is continuous at c, right? Okay, so if f is differentiable at a point, then it is continuous at that point. Now is the converse true? So So f is continuous. Now will it imply f is differentiable? No, because there are examples. So first one is, if there are some corners, then this means what? This becomes the tangent. So f dash c is what? F dash c is the tangent, slope of the tangent at that point C, right, in that graph. So if that graph becomes like this corner point, then there is no tangent at that point, then it is not differentiable at that point, but it is continuous, right? So if we take this function mod x when x belongs to R, then we will see that the graph of this function looks like this. Right? So it has a corner at 0. So it is not differentiable. And by the definition, if we see that limit x goes to c, fx minus f0 by x minus 0 has to exist if it is differentiable at 0. Right? Now what is that limit? So it is x goes to 0. This is mod x. f0 is 0 by x. Right? Now since it is approaching to 0, x goes to 0, right? And in real line, there are only two paths you can approach to 0, from left and from right, right? So this limit exists means what? This limit exists means limit x goes to 0 plus this, and limit x goes to 0 minus this exist, and they are equal. Then we will say that limit x goes to 0 mod x by x exists, right? So if this happens, this exists and this one exists and they are equal, then we will say that limit x goes to 0 mod x by x exists, right? Now when we approach from the right, that is plus means we are approaching from the right, that is greater than 0. So 0 plus mod x by x is what? So when x is greater than 0, then mod x will be only x. So it is x by x, so it will be 1. And if we approach 0 from the left, then mod x will be minus x, right? So it is 0 plus 0 minus, this is minus x by x, which is minus 1. So both exist, but they are not equal, right? So this implies limit x goes to 0 mod x by x does not exist. So this means f is not differentiable at 0. But in the other points, when x is not 0, then it is differentiable, because if x is 0, so the function fx is what? X when x greater than 0 and minus x when x is less than 0, right? So when x is not 0, then f dash x will be 1 when x greater than 0, and f dash will be minus 1 when x is less than 0. So f dash look will be this is the graph of f, and the graph of f dash will be, this is 1 and this will be -1, open, because at x equals to 0 we don't know the value, right? So this is the graph of f dash, right? Okay, so continuity does not imply differentiability, right? Now this function has only one point where it is not differentiable, but you can construct some continuous function which have finitely many points where it is not differentiable, right? You can make the corners at the integer point, right? Now your exercise is find a function which is continuous everywhere but whose derivative does not exist anywhere. At some finitely many point, countably many point, you can construct some points where you will make the corners like this one, right? But you have to find a function which is continuous everywhere on R but whose derivative does not exist at any point, right? You will try it. If you don't get the function, then I will tell you in the next class. Okay. Okay, so let's see some examples. So let's take this function fx equals to root x, where x belongs to 0 infinity, right? So find the domain of f dash. This means where f dash is valid, f dash exists. So in this function mod x, f dash is valid in r minus 0, right? At the point 0 it does not exist, so the domain of f dash is r minus 0. The domain of f dash here is r minus 0, right? Now I have to find the domain of this f dash. So let's take a point C belongs to 0 infinity, right? Now to find the derivative, we have to find this limit x goes to C, fx minus fc by x minus c, and this is what? This is root x minus root c by x minus c, and if we multiply it by root x plus c and numerator, in the numerator and denominator, then we'll get this goes to c x minus c so it is 1 by root x plus root c, right? Now if c is not 0, then this, if c is not equals to 0, then from the above line we'll get what? X goes to c fx minus fc by x minus c equals to 1 by 2 root c, right? When c is not 0, because if c is 0 then this is not valid, this is not finite number. So when c is not 0, this we get a finite number 1 by 2 root c. So this means f dash exists when x belongs to open 0 infinity. Right? At the point 0 it is not defined. It is not a finite number. So this means the domain of f is open 0 infinity. Right? Okay, let's go to the next problem. So f is a function from fx equals to x when 0 less than right. This is f, and so I have to find the derivative of f and its domain of f dash. Right, this we have to find. So first we will see that if it is continuous or not. If it is not continuous, then it can never be differentiable, right? Because if differentiable implies continuity, right? So in between 0 to 1, in between 0, 1, 2 and 3. So in between 0 to 1 it is x. So in between 0 to 1 it is continuous, and between 1 to 2 it is 2 minus x square, so it is a polynomial, so it is also continuous. And again in between 2 and 3 this is x minus x square, so it is also continuous, right? So we have to check at the points 1 and 2, right? So continuity means what? If limit x goes to that point, then fx goes to fc. If x goes to c, fx goes to fc. Then we'll say that f is continuous, right? So now here the point in 1 and 2, there are two different direction to approach 1 and 2, and for 0 and 3 there is only one direction, right? For 0 it is only the right, and for 3 it is only the left. So at the point 1 and 2 we have to find limit x goes to 1 minus fx, and limit, if this is equal, then we'll say that equal and it is equal to f1, then we'll say that f is continuous. So what is limit x goes to 1 minus fx? So 1 minus means we are approaching 1 from the left, so it is x. So limit x goes to 1 minus fx is x, so it is 1. And limit x goes to 1 plus fx is what? It is 2 minus x square, right? When x is 1 plus means when x is greater than 1 and it goes to 1. So it is also 1. And what is f1? F1 is what? Oh, sorry. So there has to be an equal sign. So f1 is what? F1 is 1. Right? So the first one is 0 less equals to x less equals to 1. Second one is 1 less than x less than 2. And the third one is 2 less equals to x less equals to 3. Okay? Now f1 is 1. So all these are equal. This implies limit x goes to 1 fx is 1 f1. This means f is continuous at x equals to 1. And for 2, limit x goes to 2 minus fx is 2 minus means this is 2 minus x square, which is minus 2, and 2 plus fx is 2 plus means x minus x square, which is also 2 minus 2 square, which is minus 2, and f2 is 2 minus is minus 2. So f is continuous at x equals to 2. So f is continuous on the closed interval 0 to 3. Right? So f is continuous in 0 to 3. Now we have to find the derivative of f. Right? Now since in the open 0 to 1 it is x, so you can derivate it by taking the differentiation. Fx is 1 in the open interval 0 to 1, right? We have to check for the end point, that is that's the break point 1 and 2. So clearly f dash x is what? F dash x is from this one, we'll see that f dash x is 1 when x belongs to open 0 1, and minus 2x when x belongs to open 1 to 2, and 1 minus 2x when x belongs to 2 to 3 open, right? Because in the corner point we don't know now, but for the interval this is the graph is what? This is x, so it will look like this one, right? Now from 1 to 2 it is 2 minus x square, so it is some parabola, I think. So it will be something like, I don't know, maybe like this one, and this is x minus x square, so it may be like this because it is continuous. Right, now we have to check at the points 1 and 2. So f dash is 1 minus 2x and 1 minus 2 when x belongs to 2 to 3. Now what is f dash 1 and f dash 2? Right. So at the point 0 and 3 also we can consider. So first let's check at the point 0. So there is only one direction from the right, so x goes to 0 plus fx minus f0 by x minus 0, if it exists or not. So this equals to, for x equals to 0, right? This is the first one. So fx is what? When x goes to 0 it is x positive, so x by 0, so it is 1. So this limit exists, means f is differentiable at the point 0, right? This implies f dash 0 is 1 and f is, this means f is differentiable at x equals to 0 and f dash 0 is 1. So at one corner, at one point we have found out. Now for the point x equals to 1 we'll consider. So for 1 there is two direction. So first check limit x goes to 1 minus fx minus f1 by x minus 1. So what is this one? So x is 1 minus. So we are approaching 1 from the left. So what is the value? So we'll take this value because it is less than 1. So it is x. So fx is now x minus, at x equals to 1, it is 1 by x minus 1. So it is 1. Now let's take x goes to 1 plus. So we are approaching 1 from the right side. So the values are greater than 1. So we'll take this value, this 2 minus x square, right? So fx is our 2 minus x square minus f1 is 1 by x minus 1. So it is 1 minus x square by x minus 1. So it will be limit x goes to 1 plus minus of x plus 1, right? So it will be minus 2, right? So limit x goes to 1 minus and limit x goes to 1 plus, these two exist but not equal. So this implies what? This implies x goes to 1, fx minus f1 by x minus 1 does not exist, right? Because the left hand limit and the right hand limit does not match. So it does not exist, means f is not differentiable. F is not differentiable at x equals to 1, right? Now let's go for the point x equals to 2. So the left hand is x goes to 2 minus fx minus f2 by x minus 2. So it will be x is 2 minus x square. f2 is what? f2 is minus 2, right? It's 2 by x minus 2. Is this right? I don't know. f2, the value of f2 is what? f2 was minus 2. So fx is 2 minus x square. Oh, sorry, it is 4. So this will be minus of x plus 2, right? So this will be minus 4. And if we approach it from the right side, so then it will be 2 plus, then we will take the function x minus x square, right? Because it is bigger than 2, minus f2 is minus 2 by x minus 2, and this value is minus x square minus plus 2 by x minus 2. If we break it, then it will be what? It will be x minus 2 into x minus 1, right? Sorry, there will be some minus, right? Then will be minus 3. Okay, so again here the left hand limit and the right hand limit does not match, so this implies limit x goes to 2, fx minus f2 by x minus 2 does not exist. So f is not differentiable at x equals to 2. And the last point is what? X equals to 3. So limit, there is only one direction, is the left, so x goes to 3 minus fx minus f3 by x minus 3 is 3 minus, this is x minus x square minus f3 is 3 minus 3 square, right? So 3 minus 9, so it is minus 6 by x minus 3, and see that this value is minus 5, right? So it exists, so this implies, so f is differentiable at 3. F is at x equals to 3, because in that domain there is only one direction. Continuity of the derivative. Yes, yes. If it is uniformly continuous, then you can extend it to the endpoints, right? That we have seen in the previous class. So for this question, so f dash is, now we have found that it is differentiable at the point 0 and 3 and not differentiable at the point 1 and 2. So the domain of f dash is what? So the domain of f dash is what? 0, close 0 to open 1, union open 1 to 2, and then 2 to 3. 3 is closed, right? Because it is not differentiable at the point 1 and 2, and it is differentiable at the other points, right? So this is the domain of f dash. Okay, you got it? Okay. Okay, so now let's see some properties of this derivative. So this is a theorem. I'm not proving it. So let I is a subset of R, but we will use this everywhere. Okay, so FG are functions and they are differentiable at a point say x equals to c, where c belongs to I. Then the followings are true. First one is alpha of f dash c equals to where alpha is a real number. Okay, and f plus g dash c equals to f dash c plus g dash c. C is, if we multiply it and then take the derivative, then it will be f dash c gc plus fc of g dash c. And for the f by g, it will be provided what? Provided GC is not equals to 0, right? Then f by g dash is this one. These are some formulas. Okay, so it was problem number 2. So let's go to the next problem. So take this function fx equals to x sine 1 by x when x not 0 and 0 when x equals to 0, right? So we have already seen that this function is continuous, right? Okay, so we have to check the derivative of f. So find the domain of f dash, right? If x is not 0, then you can clearly take the differentiation f dash, right? Then f dash, if x is not equals to 0, then f dash x will be what? This by this one, this c, it will be sine 1 by x plus x cos 1 by x into, right? So it will be 1 by x cos 1 by x, right? When x is not 0, then the derivative exists, right? But when x equals to 0, now for x equals to 0, by definition we will have to find this limit, right? If this exists, then f is differentiable at that point. For x is non-zero, if we do by this definition, then we will get this number. For x equals to 0, so this will be, so this is x sine 1 by x. At x equals to 0, it is 0 by x. So this is limit x goes to 0 sine 1 by x. Now this limit does not exist, right? So this does not exist, implies f is not differentiable at x equals to 0. So the domain of f dash is r minus 0, right? What about x square sine 1 by x? Okay, so if we take this function now, x square sine 1 by x when x is not 0 and 0 when x equals to 0. What is the domain of f dash here? It is the domain of f dash. So if x is not 0, then f dash is what? F dash x is 1 by x minus sine 1 by x, right? And when x is 0, limit x goes to 0, fx minus f0 so it will be x goes to 0, x sine 1 by x, and it is 0, so it exists. So this means this function f is differentiable at the point 0. So this means f is differentiable at all the points. So f is differentiable at in R. Right. So the domain of f dash is the whole R. Now is this function f dash continuous? So the question is this f dash continuous? So f dash exists everywhere in R. Now is f dash continuous?
Yes, ma'am, it is continuous.
Why? It is continuous at the point 0, is it? Check that it will not be continuous at the point 0. So our f dash, the function f dash is what? The function f dash is our 2x sine 1 by x minus 1 by x, and when x is not 0, and 0 when x equals to 0. This is our function now, right? Now I am saying is that this f dash is not continuous at the point 0. Continuous means what? Continuous means if x goes to 0, f dash x, if we take this, then it will be f dash 0, right? So f dash 0 is what? 0. Now see that limit x goes to 0, this function, this 2x sine 1 by x minus sine 1 by x does not exist. For this portion, this sine 1 by x, this will goes to 0, x sine 1 by x. So it is what? Limit x goes to 0, x sine 1 by x minus limit x goes to 0, sine 1 by x, right? This will be 0. But this number, this portion, this limit will not exist, right? Because limit x goes to 0, sine 1 by x does not exist. We have already seen that, right? 0 sine 1 by x. So this one, this does not exist. So limit x goes to 0, f dash x does not exist. Because for continuity, it has to exist and it has to match with f dash 0, right? If we name it as gx, then if x goes to limit x goes to 0, gx has to match with g0, then it will be continuous at that point 0. So this means f dash is our f dash is not continuous at x equals to 0. Oh, so not continuous at x equals to 0. So for this function x square sine 1 by x, f dash is f dash exists in the whole R, but f dash is not differentiable, not continuous in R, right? Okay. Now let's see the Rolle's theorem. So what is the Rolle's theorem? So Rolle's theorem says let f from closed AB to R, a function function such that f is continuous on closed AB, f is differentiable in open AB. Right. Then there exists at least one point C in open AB such that and the another condition is FA equals to FB. Then there is a point C in between A and B such that f dash C is 0. Okay, this is the Rolle's theorem. And think you can also take this FA, only FA equals to FB. Then f dash C will be 0. At least one point. Okay. And also there is a Lagrange mean value theorem. So we will write it as MBT. So this is what? This is a generalization of Rolle's theorem. So f is a function from AB to R such that f is continuous on closed AB, f is differentiable on open AB. Right. Then there exists at least one point C in between A and B such that FB minus FA equals to B minus A into f dash C. Right. See that if FA equals to FB, then f dash C will be 0. So then it becomes the Rolle's theorem. Right. So this mean value theorem is the generalization of this Rolle's theorem. Okay, let's look at the proof. It is an easy proof using the Rolle's theorem. So we'll take this function. So what is this B minus FB? So f dash C is what? F dash C is FB minus FA by B minus A. Right. So this FB minus FA by B minus A is the slope of the line segment joining. Okay, so if it is our AB and this is some graph, so if we take this, see this line segment, so this point is what? AFA and this point is BFB, right? So the slope of this line segment joining AFA and BFA is what? This is FB minus FA by B minus A, right? So this theorem tells us that there exists a point where the tangent line is parallel to this line segment, right? Because f dash C means what? F dash C means the tangent at the point C, right? So the tangent at that point will be parallel to this line segment, right? This means if we move around this line segment joining FA FB, if we move from this in this direction and this direction, we'll see that there exists a point where it will be tangent to that graph, right? Now if we see that if we move this line segment parallelly, if we move this line segment parallelly into the upward direction, then at this point, so parallelly we are moving this line, so at that point, so think at this point, so in between A and B we have found a point which is what, this point. So at this point, this is the C, so at C the tangent is what, F dash C, and which is parallel to this line segment, right? So this is the geometric interpretation of this theorem, mean value theorem. And if FA is FB, then the tangent will be what? Then the tangent will be F dash C, which will be 0, because it will be the straight line. This is parallel to the real axis, x axis. So then F dash C will be 0, right? Now if we prove this, then it is a easy proof, a two-line proof. So if we take this function phi x to be fx minus the line joining AFA and BFB, right? This line, this blue line. So the equation of this line is what? This is FA right. So if we take the difference of fx and this line segment and we are naming it by phi x, so it is what? It is into x minus a. Now what is f phi of a? Phi of a is so it is 0, this will cancel out and this is 0, so phi a is 0. What is phi b? So phi b is fb minus fa into b minus a. Now these two will cancel out, so it will be 0, right? So phi a equals to phi b. This means there exists a C in between a and b such that phi dash x is 0. So there exists C in between AB such that phi dash C equals to 0. Now what is phi dash x? Phi dash x is f dash x minus this fa will be equals to 0, so fb minus fa by b minus a into 1, right? So phi dash c equals to f dash c minus, so this is 0, implies f dash c into b minus a equals to fb minus fa, right? So this is our desired equation, right? So we have proved mean value theorem using the Rolle's theorem. Okay, now see some problems from this. So suppose f is continuous on closed AB and differentiable on open AB, and f dash x equals to 0 for all x belongs to AB, closed AB, right? Then we will see that f is constant. If f is differentiable and continuous on the closed interval, and if f dash x, the derivative is 0 on the whole interval, then f will be constant. Okay, so so it will be proved by using the mean value theorem. So let x belongs to I. X belongs to this AB. AB. So x is greater than a, right? Then we apply mean value theorem. Apply mean value theorem on this function f on the interval a to x, right? We are applying mean value theorem on this interval a to x. So there exists a point C in between a and x such that fx minus fa equals to f dash c into x minus a, right? By the mean value theorem. Now our f dash x is 0 for all x, so f dash c is also 0. So this is equals to 0. So this implies fx equals to fa, right? Now fx, x is varying in a to b and a is fixed. So fx equals to a fixed number. So this means what? This means f is, so since our this x that we have chosen here, x is arbitrary, fx equals to fa for all x belongs to closed interval ab, right? So this implies f is constant. So f is constant on this closed interval, right? So if the derivative is 0 on the whole interval, then it is constant on that interval. Okay. So let's go to the next one. So let f from open AB to R be differentiable. Okay. Now suppose there exists m greater than 0 such that mod of f dash x is strictly less than m for all x belongs to this AB, right? Then we will show that f is uniformly continuous or UC for short, on this AB. Okay. So f is differentiable and f dash is bounded by some number, right? Then we will prove that f is uniformly continuous on this open interval. So choose 2 points xy belongs to this AB such that a less than x less than y less than b, right? Now we'll apply mean value theorem on the interval x to y, right? Since f is differentiable, so f is differentiable on the closed interval x to y, right? So we obtain what? Fy minus fx equals to f dash c into y minus x, where this c belongs to what? This c belongs to open interval x y, right? So modulus of this is to mod y minus x. Now our modulus of f dash is bounded, so this is strictly less than m into y minus x. So what we get? We get f of y minus f of x is strictly less than m into y minus x, right? So this is the condition for Lipschitz continuity, right? So f is Lipschitz means f is uniformly continuous. Also, if we take a given epsilon, if we take given epsilon greater than 0, then we can choose delta to be epsilon by m, right? Then we'll get less than m into mod x minus y, which is less than m into epsilon by m, which is equals to epsilon. Whenever mod x minus y is less than delta, right? So this means since x and y are arbitrary number, so f is uniformly continuous on open AB. Now since f is uniformly continuous on this open interval, so we can extend f to the endpoint. So this actually implies limit x goes to a plus. So if we approach a from the right, this will exist, and limit x goes to b minus fx exist, right? We have already seen that in the last class, right? Since f is uniformly continuous, we can extend it to the endpoint, and the extended function is continuous on the closed interval AB, right? Okay. So let's go to the next problem. So if from R to R be a function satisfying mod of fx minus fy less equals to x minus y whole square for all xy belongs to R. Then prove that f is constant. Okay, so f satisfies this condition and we see that f is a constant function. So let's take an arbitrary point between in R. Okay, so let C be a point C be any point in R. Now for x not equals to C, so what we have? We have fx minus fc is less equals to x minus c whole square, and we can write it as fx minus fc by x minus c is less equals to modulus of x minus c, right? Now if we take the limit x goes to c in both sides, so what will we have? Have x goes to c minus fc by x minus c mod of x minus c, right? Now the left hand side is what? This is actually mod f dash c, right? Because f is differentiable. Okay. So and this is less equals to 0, right? Right? So this means, okay, if I don't write f dash c, then it is also implies limit x goes to c fx minus fc less equals to 0, and since this is a positive number, it has to be 0, right? Because a positive number less equals to 0 means what? It is 0. X minus fc by x minus c equals to 0. So, and the modulus is x goes to c, modulus of this is 0 means, so this is also 0. Right? So the derivative of f at the point c exists and it is 0. So this implies f dash c equals to 0. Right? Now since c is arbitrary point in R, so this implies f dash x is 0 for all x belongs to R, since c is an arbitrary point. Arbitrary point in R. So f dash x equals to 0, and you have already seen in this exercise 5 that if f dash x is 0 in the whole interval, then it is constant, right? So this implies f is constant, right? So if f satisfies this condition, then also f is a constant function. Right. Okay. Now let's see a different type of problem. So evaluate this number 105, right? This means approximate this number. So this is an irrational number, right? Now we'll approximate it by rational numbers. So we'll give a range of the an interval where this number belongs. So we'll use the Lagrange mean value theorem to find the approximate value of this root over 105, right? So we'll take this function, so take this function fx equals to root x, and the domain is what? Domain is a equals to 100 and b equals to 105, that is 100 to 105, right? Now apply mean value theorem on this interval AB, closed interval. So what will you get? So you get AP minus FA equals to F dash C into B minus A, where this C belongs to open AB, right? So this is nothing but AP is what? AP means root over 105 minus root over 100 equals to some F dash C into B minus A, which is 5, right? So this is 10. So F dash C is what? F dash C is 2 root C. Okay. So this is 10 plus 5 by 2 root C. Okay. Now we'll find the upper and lower bound of this root C. So where this C belongs? So C belongs to this portion, this 100 less than C. So C belongs to open AB, right? So this means 10 is less than root C, less than root over 105. Now if we replace this 105 by a square number, so the nearest is what? The nearest is 1 to 1, which is the square root of 11, right? Then we'll get what? We'll get 1 by 10 is greater than root C, greater than 1 by 11. Now if we use this one in this equation, say, so sorry, this number, this is say 1. Now if we use this one in 1, so what will you get? We'll get
Why did we choose for this less than root 121?
I didn't understand what you are saying. Hello? You can write it in the chat. So we are doing the approximation means what? We are doing it because this root over 105 is, we don't know the value, exact value of this number, right? Because this is an irrational number and the number is not a square number, right? So we are replacing it by a nearest square number. Then we can write root over of 1 to 1 is, we can write it 11, right? That's why I am replacing it, because I need an upper bound and I don't know the exact value of root over 105. That's why I am replacing it with the nearest square number, which is bigger than this root over 105, which is bigger than 105. And since root x is a continuous function and increasing, so it will be root over 105 is less than root over 121, right? That's why I am taking this. But since the difference is very big, this is 105 and this is 121, so this will give a crude result. So this bound will not be very good. So okay, let's find out the bound. So if we use this in 1, then what will we get? We'll get 105 equals to 10 plus 5 by 2 root c, which is less than 10 plus 5 by 2 into 10, and which is greater than by 2 into 11, right? Now if you calculate this number, actually then it will be 10.227 and it will be 10.25. so see this, actually since we have taken 11 in root over the bound of this 105, the difference is very big, right? So this lower bound is not a very good number. So but this upper bound is fine, okay? So we'll use this upper bound to find the lower bound. So this is okay, right? Now we'll use this to find the lower bound. How? So we have seen that C belongs to 100 and 105, right? So C is less than 105 and this means C is less than root over 105. So root C is less than 10.25. So here we have taken this number. So root C is, we have chosen this number, root C is less than 11, and now we have found that root C is less than 10.25. so this number is better, right? So since this is small, so if we use this one, this bound of C, then from 1 we'll get root over 105 is greater than 10 plus 5 by 2 into 10.25, right? And this number will be 10.2439, right? So now they are close. So what we get here is that 10.2439. So this number, this 1 root over 105 lies in between these two rational number, right? This is the approximation of root over 105. Since this is a irrational number, so it can never be some 10.5, not be equal to something. So after the point it will repeat, right? So there is always some approximation. So that's we are doing it, but by the mean value theorem. Okay. Okay, let's see some other problem. So prove that e to the power x is greater or equals to 1 plus x for all x belongs to R. With equality occurring if and only if x equals to 0. Right. So again, here we will use the mean value theorem. So this mean value theorem has many applications, right? So if x equals to 0, then from this inequality we see that both the side is 1. Both the side is 1. So equality holds. So if x equals to 0, then equality in this 1, equality in 1 holds. Right? Now let x is greater than 0. Right? Then we'll use the mean value theorem. Now apply mean value theorem on this interval 0 to x, and on the function we are taking is fx equals to e to the power x, and the domain is close 0 to x. Now if we apply mean value theorem, what will you get? We'll obtain fx minus f0 equals to b minus a, that is x into f dash c, where c belongs to in the open interval 0 to x. Right? So what is fx? Fx is e to the power x, and f0 is e to the power 0, which is 1. So this is x into f dash c, means e to the power c. Right? Now this we have to find greater equals to some. E to the power x is greater equals to something. So here we have to find e to the power c is greater than some point, some lower bound of e to the power c. Now c lies where? So 0 less than c less than x. So this means since e to the power x is a monotone function, monotone increasing, so e to the power 0 is less than e to the power c less than e to the power x. Right? So this is what? This is 1 less than e to the power c less than e to the power x. Now we need a lower bound, so we will use this one, this portion. So if you use this portion, so what will we get? We will get e to the power x minus 1 equals to x e to the power c, which is okay. So this is strictly greater than 1, means x. Right? So we get that e to the power x is strictly greater than 1 plus x when x is not 0. X is greater than 0. Okay. Okay, we choose that the domain is x belongs to 0 to infinity. Okay. Then if x is 0, then the equality holds, and x is non-zero, then it is strictly greater than 1 plus x. So this is the proof of this problem. Okay. Okay, now see this, there is a theorem, or you can write as a problem. So says 10, I think. So let f from AB to R be continuous on AB, and f dash x is greater equals to 0 for all x belongs to AB, right? Then f is monotonically increasing on this closed AB, right? If it is identically 0, then it is a constant function, and if it is greater equals to 0, then it is a monotonically increasing function. Okay, so the proof is simple. Again, the use of mean value theorem. Okay, so monotonically increasing means what? If we take any two number x1, x2, suppose x1 less than x1, x1 less than x2, then it will imply f of x1 less than f of x2, right? Oh, sorry, this is monotonic increasing, not strictly. So this is the meaning of monotonically increasing function. So first, so we'll choose two number x1, x2 in closed AB such that let's say x1 less than x2, right? So this happens. Now f is what? F is continuous, f is differentiable on the, so f is differentiable on closed x1, x2, continuous on the open x1, x2. So by mean value theorem, f of x2 minus f of x1 is some f dash c into x2 minus x1, right? Where this c belongs to open x1, x2, right? Now this implies this f dash c equals to x2 minus x1. Now f dash c is what? F dash c is greater equals to 0. So this means f of x2 minus f of x1 by x2 minus x1 is greater equals to 0. Now x2 is greater than x1, so x2 minus x1 is positive, right? So if we multiply both sides by x2 minus x1, it will be x2 minus f of x2 minus x1 is greater equals to 0. So f of x2 is greater equals to f of x1. So we have chosen x1 less than x2, and we get what? We get f of x1 less equals to f of x2. So f is monotonically increasing function, right? So this implies f is monotonically increasing on closed AB, right? Okay, now let's solve the last problem of this session. So prove that we prove this inequality when x is strictly greater than 0. Okay. Now we will use the last theorem, this theorem or this exercise, that if f dash x is greater equals to 0 in a interval, then it is monotonically increasing. We'll use this. So we'll take first the difference of the two. We'll take first difference of this one, and then we'll take the difference of this and this. Right. So first take fx equals to x by or log of 1 plus x minus x by 1 plus x. Right. So what we have to prove? We have to prove this fx is greater than 0. Right. For the left hand of this inequality. Okay, I am naming it by, this is suppose 1 equation inequality. Okay. Now what is f dash? So this f is continuous on closed 0 infinity and differentiable on open 0 infinity. Right. So when x is greater than 0, if x is greater than 0, then what is f dash x? F dash x is minus and it will be x by 1 plus x whole square. Right. Now since x is greater than 0, so this is greater than 0. Right. So f dash x strictly greater than 0. So f will be strictly increasing. So this means f is, by the previous problem, right, here our f dash was f dash greater equals to 0, that's why it is monotonically increasing. If I remove the equality sign, if f dash is strictly greater than 0, then it will be strictly monotonically increasing. Right, so our f is strictly increasing in 0 infinity. Right. So strictly increasing means, so x is strictly greater than 0, so f of 0 is strictly less than fx. So f of 0 is 0 and fx is what? Fx is log of 1 plus x minus x by 1 plus x. So x by 1 plus x is strictly less than log of 1 plus x. Right. So we get the left hand inequality of this 1. Right. Now for the right hand, we again take the difference of that two, x and log of 1 plus x. Right. So now take gx equals to, so take gx equals to x minus log of 1 plus x, where x is greater or equals to 0. Right. So the domain of this is x is greater or equals to 0. And here also x is greater or equals to 0. We are taking the function in close 0 to infinity. So again g is continuous on 0 infinity and differentiable on open 0 infinity. Right. So if x is strictly greater than 0, then g dash x is what? G dash x is 1 minus 1 by 1 plus x, which is x by 1 plus x. And since x is strictly greater than 0, this is strictly greater than 0. So again, here g is strictly monotonically increasing. Strictly increasing on 0 infinity. Right. So strictly increasing means 0 less than x implies g of 0 is less than g of x. So g0 is what? G0 is 0 and gx is x minus log of 1 plus x, right? So log of 1 plus x is strictly greater than x. So we get the right hand inequality of 1, right? So this 2 implies x by 1 plus x is strictly less than log of 1 plus x is less than x, right? So we have proved this. Okay, so this was our last problem. Now if you have any doubt, then you can ask now. Okay, so if you don't have any doubt, then we'll end this session. Okay, in the next session we'll discuss about exercise 10. Okay, in exercise 10, what is your doubt? How I have put this part, this one. This is by the hypothesis. We have already given that f dash x is greater or equals to 0 for all x belongs to AB. And C belongs to what? C belongs to, this is our AB, and x1 x2 lies between A and B, and C lies between open x1 x2. So C also lies between A and B. So this is this f dash x greater or equals to 0 also true for C, right? That's why I have written f dash C is greater or equals to 0. Okay, it is clear now, right? Okay, in the next session we'll discuss about the Riemann integral, I think. Okay, now I'll end this session. Okay, good night then.